Yeah, ladies and gentlemen, welcome to this fourth lecture on 3D coordinate systems. This time we will talk about two further representations for rotations in 3D. One is called axis angle representation, which is describing a rotation by its rotation axis and the rotation angle. And the second one is an exponential representation, which is quite nice because it's very short and actually closely linked to the axis angle representation. So let's start with the axis angle representation. Why is it possible to describe a rotation by a rotation axis and an angle in 3D? This goes back to Euler's theorem, where he says that a rotation of a sphere, that's what we are doing, onto itself can be represented as a rotation around some axis with some angle. And if we use this result, we can derive an explicit equation for the rotation matrix as a function of the axis described with a normalized vector, unit vector, and its angle by a unit matrix plus sine theta of a skew-symmetric matrix plus 1 minus cosine theta multiplied with the square of this skew-symmetric matrix. We will look at these skew-symmetric matrices soon. Now, what we do in the following is first we look into Euler's theorem and prove it. And the second is we show that this rotation matrix actually does what it should. That means it actually rotates a point around the axis with some angle. So Euler's theorem on 3D rotations says every rotation of a 2D sphere has a fixed point. Now let's assume we have a rotation matrix R. We subtract R transposed and take a half, then we get a matrix A. And we easily see that this is a skew-symmetric matrix. What is a skew-symmetric matrix? It's a matrix where if we transpose it, we get the negative matrix. So it has zeros and the diagonal, and the off-diagonal elements have different signs of corresponding entries. So why is this so? This is easily, if we take the transpose of A, we get here R transposed minus R, which is actually the negative of that what you have here. So this is easy to see. And then we can show, and this is one line, that we can exchange the product RA into AR, or if we put the R on the other side, if we multiply A from the left with R and from the right with R transposed, we again get A. Why is that so? So we just take this expression here and write it out. So we multiply A from left with R and from right with R transposed. That means we get the following, factor half here, R times R transposed minus R transposed, R transposed. So we have this expression in the brackets. And now we see that this product is a unit matrix, and also this product is the unit matrix. That means we are left with R minus R transposed, which is actually A. So this is easy to prove that this is the case. This is our first part of the proof. The second uses a lemma which is very important, which we use all the time in the future. It relates a skew matrix, an arbitrary skew matrix, and a rotation matrix. So let's assume we have the cross product of two vectors. Let's say these two. And this is the cross product which is orthogonal on A and B. Now we rotate the whole situation. Means we rotate x and y by r. Then, of course, the cross product is rotated with the same rotation matrix. And if you write that down in an equation, that means the rotation of the cross product is the cross product of the rotated vectors. Now, this doesn't help us much because we have no link of this product with the with symmetric algebra. Now, we use the skew-symmetric matrix of X, which is this matrix. So we have now here zeros on the diagonal as we expected, and we have non-zeros on the off diagonals, and we have opposite signs on the corresponding off diagonals. And now we have to take into account the indices. So we have here 1, 2, 3 in left turn rotation, so to say. And we have a change of sign starting from minus, plus, minus. This is the way how you can remember how the skew-symmetric matrix is built. And now we see that if we multiply the skew-symmetric matrix of X, that means this matrix, with some vector Y, we actually get the same expression as you know from the cross product. So if we take X 1, 2, 3 and Y 1, 2, 3 and take the product of these two vectors, you know that we get these determinants. So we get x2 multiplied with y2 minus y2 multiplied with x3, etc. So we get this expression, and now you see that this vector linearly depends on y. That means we can write this as a matrix vector product here with y, and if we now fill this matrix, we find out that we have to multiply, for instance, x2 with y3 positively, this is this one, x2 multiplied with y3, etc. That means we can write the cross product in terms of a matrix vector product using the skew-symmetric matrix of the first vector. Now, we use this equation here to derive a relation between R and the matrix S of X. So we start with this basic relation, which we know is true, and write it down using the skew-symmetric matrix. So we get R multiplied with the cross product of xy, that means S of x multiplied with y. And here we have the cross product of the rotated vector, that means S of Rx, multiplied with Ry. So this holds for all x and y. It especially holds for all y. That means the two matrices R times S of x is the same as S of the rotated vector multiplied with R. So we have this general relation, and you see it allows us to exchange rotations and skew-symmetric matrices, but we have to take into account that the arguments of the skew-symmetric matrix are not the same. So we have here Rx and here x. Or we can also write it as in this form. That means if we take a skew-symmetric matrix and rotate it from left with R and with R transpose from the right side, we get the skew-symmetric matrix of the rotated vector x. Okay, now we take these two results from the Euler theorem and these skew and rotation matrix and put them together. So because A, we have seen, is a skew-symmetric matrix, we can say it depends on some vector, 3 vector A. So because we have seen that Ra is equals AR, we have this relation. But we also have, because we have this general rule of exchanging R and S, taking into account that there is a general rotation matrix, we also know that R times S of A is the skew-symmetric of R times A, that means the rotated vector A, multiplied with R. And now you see, if we compare these two equations, there needs to be the case that A is equal Ra, which is written down here. What does it mean? If we take the vector A, rotate it, the vector stays at the same place. That means it's a fixed point. That means this vector A is a fixed point when we rotate the sphere. This is exactly showing that for any rotation matrix, we have a fixed point. Of course, the case that the matrix A is a zero matrix, that means we have a symmetric case, that A is symmetric, then the matrix A will be zero. This needs some special discussion, which is discussed in this paper here. So let's assume that we now believe that the Euler angle, the Euler theorem is true, and we have this result which I already showed. So you have here the unit matrix, here the skew-symmetric matrix of the rotation axis, the unit vector, and here the square of this matrix. And here you see terms of cosine and sine of the angle. Now, we have to observe that what happens if we take the negative sign for r and the negative sign of theta. What happens? Now, the sign of minus theta is minus sine of theta, and the skew-symmetric matrix actually also changes the sign. So this stays the same. And now the cosine of the negative angle theta is the same as the cosine of the angle. And because SR is a square matrix, it also doesn't change its sign. So actually, if we change the sign of both, we don't change the rotation. This is very plausible. So let's assume we have the rotation axis upwards and a positive rotation in this direction. Now, what happens if we have the rotation axis described with the opposite vector? We have to rotate in the opposite direction in order to get the same rotation. So this is very intuitive. Now we prove that this rotation actually fulfills all that properties which we want. So we first show that the rotation axis is R, that R is a rotation matrix, and that the angle of the rotation is theta. So we use these properties that S is the skew-symmetric matrix, and we use this dyadic product of R and R transpose, which actually has the R1 square, R2 square, R3 square on the diagonals, and the products of the entries of R on the off diagonals. It's a symmetric matrix. And these two matrices are closely related, and I collect some relations between these two matrices on the next slide. So, the first thing is we see that D is a symmetric matrix. Now, what happens if we square D? We see that it is the same as D, so it's an idempotent matrix. So if we multiply this out, we see that R transposed R, because it's a unit vector, is 1, so we actually get R transposed. We have seen already that S is antisymmetric, and it is related to the cross product. So if we multiply the matrix SR with this vector R, it's a cross product of two identical or parallel vectors, and of course this is 0. Then we have an interesting relation, which I leave to an exercise, that the square of SR is identical to minus unit matrix minus D, so SR square is a symmetric matrix. And we can also easily show that if we take SR to the third, we find out it's SR except of the sign. And if we take the SR to the fourth power, we find out it's the negative of SR square. And of course, generally SR multiplied with D is 0, because D is R times R transpose, so we have SR times R, which is 0 multiplied with R. So we use these properties in the following. The first thing is that we rewrite the rotation matrix. So we started with this definition, and we want to show that this holds. If this holds, we can take SR squared to be minus I minus D, and rearrange the terms and get here a symmetric part with the unit matrix and the D matrix, and the unsymmetric part with the skew-symmetric matrix S. So the sine theta SR part stays the same, and the I plus something plus S square is replaced by some factor multiplied with I plus something multiplied with D. So this is the symmetric part. This is just a rewriting, a simple rewriting. And we now can also go further and ask what happens if we don't make the whole expression depending on r and theta, but only on the product. Then we get the following result, which is already shown by Rodriguez in the mid of the 19th century. So we take the rotation vector, which is the product of the direction vector r multiplied with the angle. So it shows the axis, and the length of this vector is proportional to the rotation angle. So we easily can derive the rotation angle by just taking the length of this vector, and we can derive the rotation axis by just normalizing this vector to length 1. And then we can use this first relation and say it's I plus sine theta multiplied with the skew symmetric of theta. So in this case, here we have the angle, here we have multiplied with the angle, so we have to divide by the angle, and here we have the square of the matrix, so we have this multiply with the square of the angle divided by the square of the angle. So this is the same description of the rotation depending on the rotation and the angle, eliminating the sign problem which we had because we only work with the product. All three representations are useful depending on what type of algebraic derivation you want to do. So let's go to the proof. Let's start with this rotation matrix I plus sine theta s plus 1 minus cosine sr square. And we first want to prove that if you have any point D on the rotation axis, that means if you have r, the unit vector, you can multiply it with any factor mu. That means this is some arbitrary point on the rotation axis, and we show that if we multiply d with r, that means we rotate d, it stays at the same point. That means it is a fixed point. How do we see this? Now just multiply this expression with d. So we see here I multiplied with d, which leaves us with d. And then we have here the multiplication of the skew-symmetric matrix of R multiplied with D, and because D is parallel to R, the cross product of R and R0, and we have the same here. So just these two, the second and the third term cancel, and we are left with the rotated vector is identical to itself. So all points on the axis are fixed points. The second, what we want to show or discuss is that R is a rotation matrix. That means if we multiply R with R transposed, we get the unit matrix. So we just have to look what is R transposed. So unit matrix stays. The skew-symmetric matrix, if we transpose it, we get the negative matrix. And we know that SR is symmetric, so this also stays. So we just have a sign change here. And it's a simple exercise to just multiply these two matrices in order to show that this product is the unit matrix. So we are left with the problem whether the rotation matrix actually rotates around R with the angle theta. So have a look at this figure. We have here the origin, we have here upwards the rotation axis, we have some arbitrary point Q outside this rotation axis with the vector direction vector q, the vector q. And if you rotate it by some theta, it turns around the axis to this point q prime, which has the vector q prime. And now we separate this vector in two parts. One is parallel to the rotation axis, which is p, and one which is orthogonal to the rotation matrix, which is O. And now we, of course, would say P should not change after the rotation. Of course, it doesn't. And O rotates into O prime. And we then want to show that the angle between O and O prime actually is the angle theta. So we have to show that. So now let's have a look how this can be proven. We just do the following. We multiply the vector q of our given point with the rotation matrix to get q prime. So we have this expression, that's the rotation matrix with 3 terms multiplied with p plus o. So we multiply each of these terms with p plus o. So we first get cosine theta multiplied with p plus o. Then we have 1 minus cosine theta multiplied with r transpose times p plus o. And we have finally sine theta, and now we have the product of this q-symmetric matrix with the vector p plus o, that is the cross product of r with p plus o. So at this point we have nothing saved. Now we have a look at a simplification. So the first part is that we say p is equal to lambda times r, which is fine. Now we have this expression. This consists of 2 parts. So the first part is r transposed p. Now, what does that mean? Yeah, this is very easy. We have p equals lambda times r. R transposed r is 1, so we are left with 1 lambda times r. Lambda, actually 1 minus cosine multiplied with r. Now what is with the O term? The O term is orthogonal to the rotation axis. That means R transposed O is the dot product of 2 orthogonal angles, two orthogonal vectors. That means this is 0. So we have no part with the O here. But we of course have a O part here, which is actually the cross product of S with O, because P is parallel to R. That means the cross product of R and P is 0. So we have a reduced expression here. And now we have a look what happens in the next step. We have here cosine theta multiplied with lambda r. We have this same expression here, cosine theta times lambda r. So we are left with lambda times r, which is actually the p prime. Well, this is fine because p moves to p prime. That's a fixed point. And we are left with the expression with respect to O. So we have cosine theta multiplied with O. This is this part. And we have the sine multiplied with S cross product of O. So we have this expression for the rotated part O. That is O prime. Now we take this part and want to know what is the angle between O prime and O. So we just take the dot product between O prime and O. So we take this expression here and make the dot product. So the first part is cosine theta multiplied with the dot product of O and O. That's the length of at O, because O is the vector with itself. So we have this expression. And the second part is a cross product with having O in here and O outside as dot product. So this part is 0. And we are left with this should be square. So we have here O prime dot O is O dot O multiplied with cosine theta. That means actually the angle between these two vectors O prime and O is theta. So we are done and know that we can use this rotation matrix for our purposes. Okay, next problem is we want to invert this. So let's assume we have a rotation matrix given and the axis and the angle are unknown. We want to derive the axis and the angle. Now let's start with the angle. So take the rotation matrix and write it down explicitly in this form. So we have the symmetric part here and the asymmetric part here. And now we look at the trace of the rotation matrix. So that's the sum of the traces of these 3 elements. The trace of cosine theta times I is the cosine theta multiplied with the trace of I, which is 3. So this is 3 times cosine theta. And here we have the matrix D. The D has as diagonal elements R1, R2, and R3 squared. So the diagonal terms add to 1. That means the trace of this matrix is 1 minus theta. And the last trace is 0 because S is a skew symmetric with zeros on the diagonal. So that means the trace of a rotation matrix is related to the angle theta by 1 plus 2 cosine theta, because we have the 3 cosine theta plus 1 minus cosine theta. And this allows us to derive theta. Yeah, we take trace minus 1, divide by 2, and take the arcus cosine and get the theta. Now we have to remember we shouldn't use the arcus cosine for determining an angle. That means we would like to use the double-valued function arcus tangens. So we need the sine, and this should be derivable from the asymmetric part. So let's take this q vector A from A R minus R transposed. This vector A is the same vector as we used in the proof for the Euler theorem, except for factor 2. So if we write this down, we find out that the skew symmetric part appears twice. So we have 2 sine theta multiplied with SR. Now we know that if we have a 3 by 3 matrix, which is Q, we can extract the 3 elements of the causing vector. That means we can write down the 3 elements of A using the 2, 3 element, the 3, 1 element, and the 1, 2 element, and get 2 times sine of the theta multiplied with the rotation vector. So this allows us to get the sine of theta, because R is a unit vector. That means we can derive the angle theta from the arcus tangens with 2 arguments as the absolute value of A, which is 2 sine theta, and trace of R minus 1. Trace of R minus 1 is 2 times theta. So this is an easy way to get the angle in a numerically stable way from the rotation matrix. We will come back to this routine later. That means we have a very simple way to get the rotation angle. Now we want to look at the rotation axis. That's a little bit more tricky, because it starts with the simple case that the rotation is 0. That means we have the rotation matrix is a unit matrix. What is the rotation axis? Now, you can take any rotation matrix and don't rotate and get the unit matrix. So the rotation axis is not determined. You can choose any. This is easy. The second part is a little bit more involving. So in case we have a 180 degrees rotation, then we take this form. If we have 180 degrees rotation, the cosine of theta is minus 1. So we get this value. This is minus 1, so we have here 2, and the sine part, the sine is 0. So we have the following relation, that the rotation matrix is minus 1 times the unit matrix plus 2 times the diodic product dr. This allows us to derive dr. We just take r plus I and divide by 2, and we get the matrix D. This diodic product, the product of a vertical vector and a horizontal vector, it has rank 1. That means all the rows are proportional to R. All the columns are proportional to R. That means we can take any row or column and derive R. And of course, we take that row or column where the largest value appears in order to get a stable solution. So this is a way to derive the rotation matrix if it is symmetric. And for instance, if you have a rotation around the x-axis by 180 degrees, we get this rotation matrix minus the unit matrix plus 2 times the r times r transposed, which is this matrix. This is D. And if we sum them, we get the rotation matrix 1, minus 1, minus 1. It's symmetric. And if we would have given this matrix and would like to know the rotation matrix, we would derive the matrix D, which is this one. And of course, we take this column vector, normalize it if it would be not already be normalized. So we get the rotation axis here as the first column of D. So this is easy. And in case the angles are neither 0 nor pi, 180 degrees, we just take the relation between r and a. A was minus sine theta multiplied with r. So we just have to normalize this vector a and get the direction vector of the rotation axis. And of course, this is also stable. But of course, if we do it in programming, we have to not check for 0 or pi, but we have to check whether the value is close to 0 or close to pi with some tolerance depending on the numerical accuracy. Okay, take the following rotation matrix with only ones, and we would like to know what is this rotation about. So the first thing is that we see that the A is the negative value of this, the negative value of this. So we have the vector A to be minus 1, minus 1, minus 1. That means the rotation matrix is the normalized vector we have to divide by square root of 3. Now what is the angle? We see it's the length of this vector multiplied with the trace minus 1. The trace is 0, minus 1 is minus 1. And if we calculate this, we get a rotation angle of 120 degrees. Okay. Can you visualize this? Yes, this is actually what is going on here. So you have a cube with x, y, z looking halfwards upwards. That means the vertical axis of this plot is in the direction plus 1, plus 1, plus 1. And if we take the negative value, we get actually the rotation matrix, the rotation direction. That means the rotation is going through the lowest and the highest point of this cube in this position. And the rotation angle is 120 degrees. That means, what does that mean? We rotate from here to here. That means from one corner of the cube to the next corner of the cube in the same height. So this is, so to say, the classical rotation of a cube, which you usually would not imagine that it would occur. Usually you think about 90 degrees rotation. So you can rotate a cube by 190 degrees and it is mapped into itself. Now let's go back to the rotation matrix with 1, minus 1, minus 1. And we have seen that with the previous example that the diagonal element, this diagonal matrix actually leads us to that this is a rotation around the x-axis by 180 degrees. We saw this in the previous case. Okay, what did we see in the last few slides? We saw that the rotation with axle and angle can be represented by either this expression or this expression, depending on whether we make it dependent on r and theta or on the product. We have seen that this first description is not unique, so if we change the sign of r and theta, we get the same rotation. Of course, this doesn't change the rotation vectors boldface theta. And of course, we know that if we add 2 times 360 degrees multiplied with some arbitrary integer, we get a rotation, let's say, of 10 degrees, or I can't turn my hand round enough, or 370 degrees. This of course leads to the same rotation. That means we will not be able to recover rotations which are larger than 360 degrees, though they of course occur in practice if you have a rotating object. So this was the representation of a rotation matrix in axis angle form, and now we have a look at an exponential form of the rotation matrix. So we start with the rotation vector theta, which is the product of the angle and the rotation axis, normalized vector, or with these three elements. And then I postulate that the rotation matrix, depending on this vector, is the exponential of the skew-symmetric matrix to that vector. Okay, we need to imagine what is the exponential of a matrix. Okay, we generalize the infinite sequence of the exponential form to matrices. So we start with the unit matrix, the skew-symmetric matrix, 1 divided by 2 factorial multiplied with the square, 1 over 3 factorial multiplied with s theta to the third, etc. So this is the definition of the exponential of some arbitrary matrix, and it's defined for all matrices, all square matrices. Now, what does this rotation mean? Is it a rotation matrix? We have to find out. Okay. The first thing is that we find out that if we take an arbitrary point on the rotation axis, this is a fixed point. So if we multiply the rotation matrix with theta, we get theta plus skew-symmetric matrix of theta multiplied with theta, which is 0. Again here, 0, 0, 0. So actually theta is a fixed point, or any multiple of theta. And the question is, so we have a fixed axis, but what happens with other points? What happens with the angle? Okay, what we want to do is the following. We write this infinite series in a little bit different form. So we collect the odd terms, SR, SR to the third, SR to the fifth, etc., and the even parts, which is S theta square, S theta to the fourth, etc. And we take into account that the square of SR and the fourth power are related by a negative sign. And that we have take the third power, we have minus SR. So what happens with SR to the fifth? It would be minus SR to the square multiplied with S, so it would be SR third, which would be minus SR. So SR to the fifth is the same as SR. So we have a series which actually, if we take the third power here, we get theta times SR minus 1 over 3 factorial multiplied with this angle theta multiplied with SR to the third, and that's the reason why we have to take this minus sign here, plus sign, and it's alternating. And we have the same situation for the square, so this is the original term. Then we have here with the 4 factorial and the fourth power, and we have seen that this is the negative square. So we have here a series which only depends on theta and SR. And here, which only depends on the even terms in the exponent of theta multiplied with SR square. So we can take this out and have R is the unit matrix plus the series theta minus 1 over 3 factorial theta to the third, etc., multiplied with SR. And here the even terms multiplied with SR square. And now we remember that this first series is identical to the sign of the argument. And this second part, except for the 1 and the minus sign, is identical to the cosine of the argument. That means actually what we achieve is that this rotation matrix is I plus sine of theta multiplied with SR. And here we have this series on the other side, 1 minus theta multiplied with SR square. Aha! That means the rotation matrix, which we defined using the exponential of the skew-symmetric matrix, and the definition of the rotation matrix using axis and angle, using the product, are exactly the same. So we have the following interesting relation. You define the rotation matrix depending on a rotation angle, a rotation vector. That means the rotation direction multiplied with the size of the rotation as the exponent of the skew-symmetric matrix. We don't write that out at this place in order to keep things short. And we know how to calculate this without working out the series because we did the theory before. So this exponential can actually be calculated with this short form. You see all the terms which are higher than third power are cancelled because they are captured in these sines and cosines here in the coefficients. That means the infinite sum is shortened to 3 terms. And of course, this definition of the rotation matrix is the shortest you can imagine because you only need 3 letters to write things down. And we have the advantage that the definition actually is related to the axis angle representation. That means we can even interpret what is going on here, what this vector theta means. We also can invert, of course, the exponent. There's a corresponding definition for the logarithm of a matrix. I don't write down the series, but of course, by analogy, you find out that the skew-symmetric matrix of theta is the logarithm of the rotation matrix based on theta using the rotation vector. We, of course, don't work with the series, but we use the algorithm which we derived before for deriving the axis normalized vector and the angle in order to actually get the rotation vector if you have given the rotation. So this is something which you, if you want to write some nice paper and it should look very scientifically, you write log of r and you say this is a skew-symmetric matrix, and then you can determine the theta, but actually you have an algorithm which uses these cases which we discussed up now. In MATLAB, you have routines exp of matrix, which takes the matrix as argument, and the same for the logarithm with matrices, which takes as argument a matrix. And it works nicely in case you have certain conditions here for the logarithm that the matrix has certain properties which I don't want to discuss at the moment. So we discussed axis angle and exponential representation. The axis angle representation is useful if the rotation axis is really given by the hardware. So if you have some object which is some instrument where you have a rotation axis and you want to describe the motion in this coordinate system, you can use these equations. It's easy to visualize because you have the rotation axis and the angle. You have some ambiguities. First one is that you have the sign ambiguity for the rotation direction and the angle. And of course, if you have if you add multiples of 360 degrees to your angle, you of course get the same rotation matrix. That means you cannot recover rotations outside your given range in 0 plus 2 pi. The exponential representation certainly is the shortest interpretable representation. So it's not only the shortest, but it's also interpretable because it's directly related to the axis angle representation. You could also define the exponential representation using the axis angle representation because the equations are exactly the same, and you have just the periodicity ambiguity for the angle in this case. Okay, these were two representations which used angles and axes. And all the representations which I discussed up to now are either highly redundant, like the rotation matrix, or contain cosines and sines, which is sometimes not quite comfortable. And therefore, next time we will discuss what is called quaternions. These are 4 vectors. And these representations are doing without any trigonometric terms. And we look at the concatenation of rotations if we want to do the concatenation not based on rotation matrices, which we did, but on their parameters. Thank you very much for listening, and until next time.